Hello, and welcome to the Chapter 4.3 video lecture on homogeneous linear equations with constant coefficients. So in the previous two sections, we learned how to combine solutions to the general homogeneous equation with a particular solution to the given equation to get general solutions to linear differential equations. And in 4.2, we learned reduction of order, which can generate new solutions from a given solution to get a full fundamental solution set. But we had not yet learned how to get any solutions from scratch. And in this section, we're going to learn how to get solutions from scratch, and then we can combine that with what we learned in 4.1 and 4.2 to generate fundamental solution sets and solve for the general solutions of linear differential equations. So suppose that we have a linear homogeneous differential equation, an times the nth derivative of y plus an minus 1 times the n minus 1th derivative of y, etc., where each of these coefficients is constant. So in other words, not a function of x. Let's see what happens if we substitute y equals e to the rx into this for some unknown constant r. So in other words, we're just going to kind of guess that e to the rx is a solution for some r. Well, then we'll have an times the nth derivative of e to the rx plus an minus 1 times the n minus 1th derivative of it, etc., equals 0. Okay, so let's evaluate this from right to left. So that term is itself. What is the first derivative of e to the rx? Well, r is a constant, we just pull it down. Okay, what is the second derivative? Well, we just pull down the constant again. We already had an r down there, though, so now it's r squared e to the rx. For the third derivative, we pull down r 3 times, we'll have an r cubed in front, etc. So we have that. Now, notice that we have e to the rx's in all of these terms. So we'll factor out that e to the rx, and we'll have that as the left-hand side. This guy here is called the auxiliary polynomial. Okay, and if it satisfies, if e to the rx satisfies this differential equation for all x, and that means that this must be equal to 0 no matter what x is. And in particular, e to the rx is never 0. So note that this is not equal to 0. And if a product of two things is 0, but one of them is not 0, then that means that the other part must be 0. So this must be a 0 times a non-zero is 0. So we must have from this that this auxiliary polynomial, as we call it, equals 0. And in fact, one can do this in reverse, beginning from this being true and going up a step, up a step, up a step, and getting that if r satisfies this auxiliary polynomial, then also e to the rx is a solution to the differential equation. So what we have shown is that y equals e to the rx is a solution of a homogeneous linear differential equation with constant coefficients, if and only if r satisfies this auxiliary polynomial, also known as the auxiliary equation. So great, we can find a solution of a linear homogeneous differential equation with constant coefficients by solving this polynomial, getting what r is, and then e to the rx is a solution. So let's illustrate this. Let's solve this differential equation. So first, what's the auxiliary equation here? That would be r squared minus 5r plus 6 equals 0. We want to solve for r. That is r minus 2 times r minus 3 equals 0. So r is equal to 2 and 3. So that means that e to the 2x and e to the 3x are solutions. And those two neither is a scalar multiple of the other. So those are linearly independent and thus a fundamental solution set. So therefore, the general solution to that differential equation is c1 e to the 2x plus c2 e to the 3x. So you just solve the auxiliary equation, get your R values, and those are solutions. And if you have as many solutions as the order of the differential equation, then it will be a fundamental solution set. This was second order. We ended up with 2 distinct linearly independent solutions, so we had our full solution set. Go ahead and try your hand at this. Take a moment, find the auxiliary equation and solve. So the auxiliary equation here is r squared minus 1 equals 0, i.e. r minus 1 times r plus 1. So r is equal to plus or minus 1. So to be clear, e to the 1x and e to the negative 1x, those 2 solutions are those r values, are solutions. And e to the x and e to the negative x, neither of those is a scalar multiple of each other. That is a fundamental solution set. So the general solution is c1 e to the x plus c2 e to the negative x. What about this one? So what's the auxiliary equation? That is r squared minus 2r is 0. That factors as r times r minus 2 is 0, so r is equal to 0 and 2. So thus, e to the 0x and e to the 2x are solutions, but e to the 0x is 1. Anything to the 0 is 1. So 1 and e to the 2x are solutions, and they are linearly independent. E to the 2x is not a scalar multiple of the constant function 1. Remember, that's not a number, that's the function y equals 1. So the general solution is y is c1 times 1 plus c2 times e to the 2x, which is c1 plus c2 e to the 2x. So point of that example is if r is 0, that can certainly happen, and it's not really a special case. It just becomes 1, and you wind up with something like that. Now, here's a case that's a bit different. What's the auxiliary equation here? Well, we have r squared minus 2r plus 1 is 0. That factors as r minus 1 squared is 0. So r is 1. So we got only one r value here. It has multiplicity 2. Yes, but it's only one r value. Remember that the multiplicity, that means the power of the root in the polynomial. So we say that this is of multiplicity 2, just to remind you of what that means. So that means that e to the 1 times x is a solution. And does that mean that y equals c1 times e to the x is the general solution? No. That's because this was a second order differential equation, so it needs a 2-dimensional solution set, i.e. 2 arbitrary constants, not just 1. So we need some other solution that is linearly independent from just e to the x. And how do we get that? Because the only solution of the form e to the rx is where r is 1. Well, we learned in chapter 4.2 how to get another linearly independent solution to a differential equation given one of them, and that was a reduction of order. So we can take this, plug it into the reduction of order formula, and wind up with another linearly independent solution, and thus the full solution set. Fortunately, when we plug it into the reduction of order formula, we always wind up with the same thing in terms of what r is. And that is, if r is a repeated root of the auxiliary equation, then yes, e to the rx is a solution, and then reduction of order gets us that also x times e to the rx is a solution. So for this one, we got that r minus 1 squared is 0, so r is equal to 1 with multiplicity 2. So 2 solutions are therefore e to the x and also x times e to the x. Again, there's a 1 there, that's our Rx up there. And those two are linearly independent and thus form a fundamental solution set. Now we have our two linearly independent solutions for a second order differential equation. So that's all of them, in the sense that our general solution is C1 e to the x plus C2 x e to the x. So from the root alone, we only got the e to the x part, and then the reduction of order, which always yields that we just stick an x in front for the repeated roots, gets us that other component of the general solution. Let's do another example, this time with a third order differential equation. So the auxiliary equation here is r cubed minus 5r squared plus 8r minus 4. We want to solve for what r values satisfy that. You can do testing and polynomial division and verify that this is r minus 2 squared times r minus 1, and thus r is equal to 1, or r is 2, the latter with multiplicity 2, since that root has a square. So what is the general solution here? It is y is c1 e to the x plus c2 e to the 2x. And then because we have this multiplicity 2 for that root of 2, plus c3x e to the 2x. So this part here, remember that's e to the 1x coming from this root. And then these parts here come from that root with the multiplicity of 2. And indeed, that is 3 linearly independent solutions for a third order differential equation. Now, what if there's a triple root? Well then, not only would x times e to the rx be a solution, but also x squared times e to the rx. And if it's a quadruple root, also x cubed times e to the rx. So here, for example, the auxiliary equation, that would be r cubed minus 3r squared plus 3r minus 1 is 0. That factors as r minus 1 cubed is 0. So r is equal to 1 with multiplicity 3. So what is the general solution? It would be c1 times e to the 1x plus c2 times xe to the 1x plus c3 x squared times e to the 1x. r equals 1 has that multiplicity of 3, and that generates a three-dimensional solution set corresponding to that root, which we get just by sticking x and x squared in front, or the other linearly independent solutions. So this is our general solution to this differential equation. 3 linearly independent solutions, third order differential equation. And as this example illustrated, this method for repeated roots can be combined with other roots that might be single roots in this way. So we have this one solution for this one root of multiplicity 1, and then we have these two solutions for this other root of multiplicity 2, generating in total a three-dimensional solution set for that third order. All right, so we now know how to deal with all cases where the auxiliary polynomial has exclusively real roots, but some polynomials have complex roots. Before we get into this, we need to do a review, or if you haven't seen them before, simply teach complex numbers. So what is the square root of -1? Well, you can't take the square root of a negative, you might have learned. That's because -1 squared is +1. This has no real solution. And what we do is we define I to be such that I squared is equal to -1. So I is called the imaginary unit. And definition, a complex number is one of the form a plus bi, for a and b real numbers. So for example, 2 plus 3i is a complex number. And we can multiply and divide complex numbers and add them. So for example, 2 plus 3i plus, 3 minus 5i. We add the respective real and imaginary components. So gather the real parts together, gather the complex parts together, and that would be 5 minus 2i. And we can multiply them. So for example, multiplying these two complex numbers, all you do is you FOIL it out. So foiling this out, we have 6 minus 10i plus 9i minus 15i squared. That's just standard foiling. And that 15i squared is 3i times minus 5i. But what is I squared? Well, I squared is -1. So this is 6 minus I minus 15 times -1. That minus I is -10i plus 9i. And 6 plus 15 is 21. So the answer there would be 21 minus I. So that's adding and multiplying complex numbers. You can also divide them using conjugates, which we'll get to in a bit. The most relevant thing for us, though, will be regarding finding roots of auxiliary polynomials, which may be complex, and how to deal with those regarding finding corresponding solutions of the differential equation. So suppose that we get an auxiliary polynomial that looks like this. Well, we need to find the roots. So what two numbers added together are -4 and multiplied are 13? Well, none come to mind. So we need to use the quadratic formula. Remember what the quadratic formula is? I remember it with this annoying tune. It goes to the tune of Pop Goes the Weasel. X equals -b plus or minus the radical b squared minus 4ac all over 2a. I'm sorry for subjecting you to that. So plugging in here, we have x is -4 plus or minus the radical of -4 squared minus 4 times 1 times 13 all over 2 times 1. So we have 4 plus or minus the square root. Here we have 16 minus 52 is -36 all over 2. And the square root of -36 is 6i. As you can verify, because 6i squared, let me write this up here. So what is 6i squared? Well, that is 6 squared times I squared, but I squared is -1. So this is 36 times -1 is -36. So since 6i squared is -36, square root of -36 is 6i. And in general, whenever you take the square root of a negative, you just look at what the square root of the positive part of that is. Square root of 36 is 6, and then you stick an I by it. And we can continue to simplify this. 4 over 2 is 2, plus or minus 6 over 2 is 3. So we have 2 plus or minus 3i. These are two distinct roots for this quadratic. It's 2 plus 3i and also 2 minus 3i are the two solutions. And this is what is called a conjugate pair. The conjugate of a complex number alpha plus beta I is denoted with a bar over the complex number and is alpha minus beta I. You might remember conjugates from Calculus 1. They were useful in the sense of something like 5 plus square root 2 to rationalize quotients and limits, and is defined analogously for complex numbers. And here's a theorem. if you have a polynomial with real coefficients, and if alpha plus beta I is a root, then so is its conjugate alpha minus beta I. In other words, complex roots of polynomials with real coefficients always occur in conjugate pairs, alpha plus or minus beta I. And we saw that over here, this is a conjugate pair. The two roots are 2 plus 3i and 2 minus 3i. Now, we'll be taking e to the rx, or r a complex number. So what we need to know is, what is something like e to the 2i? How do you take a complex exponent? That's just an example. The point is, e to the rx will be doing that per our central theorem, where if r is a root of the corresponding auxiliary polynomial, then e to the rx is a solution. And if that root r is complex, then we need to take e to a complex number. To answer this, we'll need to recall the Taylor series for e to the x, sine x, and cosine x. These should look familiar. And looking at these, there seems to almost be a relation. Like, the sine x parts look like every other term of e to the x, except with these minus signs occurring every other term. Similarly, the cosine x, it looks like also every other term of e to the x, except with these negative signs. Let's see what happens if we take e to the power of an imaginary number. So like e to the power of beta I, where beta a real number. Well, plugging in, that will be 1 plus beta I over 1 factorial plus beta I squared over 2 factorial plus beta I cubed over 3 factorial plus etc. Okay, so that's 1 plus beta I. 1 factorial is 1. What is I squared? Well, I squared is -1, so this becomes negative beta squared over 2 factorial. What is I cubed? Perhaps we should write this out up here. So we know that I squared is -1, and therefore I cubed, well, that's I times I squared, and that's negative I, and therefore I to the 4th, that's I times I cubed, which is I times negative I, which is negative I squared, which is -1, which is 1. So it cycles back when you get to I to the 4th. So the point is, that's I, this will be -1, that's negative I, that's +1, and it repeats. So then we have a negative beta cubed I over 3 factorial. I to the 4th is +1, so that's just beta to the 4th over 4 factorial. The next term, I to the 5th, that will be just I. The next term, I to the 6th, that's the same as I squared. That's -1, etc. But this is going somewhere quickly, I promise. Let's gather together the real terms and imaginary terms. The real terms look like this. And the imaginary terms, we gather together everything with an I by it and factor out the I. That's a beta minus beta cubed over 3 factorial plus beta to the 5 over 5 factorial, that guy, minus etc. And we factored out the I. Now, this part, 1 minus beta squared over 2 factorial plus beta to the 4th over 4 factorial. What does that look like? What is it? Well, look at this. That is literally cosine of beta. And these terms, beta minus beta cubed over 3 factorial plus beta to the 5 over 5 factorial, x minus x cubed over 3 factorial plus x to the 5 over 5 factorial. So that is sine of beta. So this is cosine of beta plus sine of beta times I. That I is still there. So we have cosine beta plus I sine beta. So e to the beta I is cosine beta plus I sine beta. I was using the variable beta because of the alpha plus or minus beta I part for conjugate roots. It's typically expressed with the theta, though it's the same thing. What we have shown is that e to the I theta is cosine theta plus I sine theta. That is precisely what we showed here. E to the beta I is cosine beta plus I sine beta. This is known as Euler's formula. And what we're interested in is what if R is equal to alpha plus or minus beta I? Well, then what we want is e to the Rx, right? Which is e to the alpha plus or minus beta Ix, which is e to the alpha x times e to the plus or minus beta xi, which is e to the alpha x times, by Euler's formula, cosine beta x plus I sine plus or minus beta x. And recall, sine is an odd function. So sine of negative x is negative sine x. So in other words, we can pull out this plus or minus sign. And this is e to the alpha x times cosine beta x plus or minus I sine beta x. And that's true if we were solving differential equations over complex numbers. This is a perfectly valid way of writing the two linearly independent solutions. However, we want solutions over real numbers, and the thing is that we can combine and scale the two solutions and scale them by I in order to isolate the e to the alpha x cosine beta part and the e to the alpha x sine beta part. So for example, adding together these two solutions would get 2 e to the alpha x cosine beta x. But we don't care about that scalar multiple in front because we just want a solution. Do you see how adding them together would get that? We have cosine plus I sine and cosine minus I sine. So adding them together, the I sines cancel out. And then we have two cosines. So we end up with 2 e to the alpha x cosine beta x, because the plus I sine and minus I sine cancel out when you add them together, the two solutions. And similarly, then we can isolate the e to the alpha x sine beta part, scale it by I, and get the other solution. So what we wind up with is that if alpha plus or minus beta I are complex roots of the auxiliary polynomial, then both e to the alpha x sine beta x and e to the alpha x cosine beta x are solutions of the differential equation. So these are the two linearly independent real solutions corresponding to this conjugate pair of complex roots of the auxiliary polynomial. So, for example, what is the general solution to this differential equation? Well, the auxiliary polynomial is r squared minus 4r plus 13 is 0. And we solved earlier via the quadratic formula that r is equal to 2 plus or minus 3i. So therefore the general solution is c1 e to the 2x sine 3x plus c2 e to the 2x cosine 3x. That is what we have shown via Euler's formula, which we derived for the two real linearly independent solutions corresponding to this conjugate pair. That real part 2 is there and there. The complex part 3 is there and there. And that's a two-dimensional solution set for a second order, so is complete and the full solution. Let's do another example. This will illustrate just a slightly different thing that might happen. Let's solve y double prime plus y is 0. So what's the auxiliary equation? That would be r squared plus 1 is 0. We actually don't need the quadratic formula here. We could do quadratic formula, but this is r squared is negative 1. And if r squared is negative 1, then r is plus or minus the square root of -1, so r is plus or minus I. Okay, but how does this theorem apply? What's alpha? What's the real part? Well, it's 0. So we can write this as 0 plus or minus 1 times I, and that gives us our real and imaginary part. So that is c1 e to the 0x, because of that real part 0 times sine of 1 times x, that 1 is that one there, plus c2 e to the 0x times cosine of 1x. But what is e to the power of 0? It is 1. So this is just y is c1 sine x plus c2 cosine x. So if you wind up with a root that is strictly imaginary, it can still be written as a complex number in that way, and the same usual formula that we've derived applies. And that's a two-dimensional solution set for a second-order differential equation. And you can verify indeed that, for example, the second derivative of sine plus sine is 0, because the second derivative of sine is negative sine. So we have negative sine plus sine is 0. Same with cosine, and therefore any linear combination of them. Now, a auxiliary polynomial could have both complex and real roots. And in that case, we combine them in the same way that we did earlier if it has a repeated root and then also another root. So for example, this equation, the auxiliary is r cubed minus 4r squared plus 9r minus 10 is 0. You can solve for r manually here using what you learned in pre-calculus about finding a root by inspection and factoring it out via polynomial division. You did all that for a reason. I'll trust that you know how to do that in principle, but if you want to verify your work, or you know how to do it and you just don't want to spend too much time doing it, you can also ask Wolfram alpha. So I inputted this auxiliary polynomial right there, and it factors it for me right there. And that means that we have a root of 2, and in this part, it does not factor over the real numbers. One can use the quadratic formula on r squared minus 2r plus 5 and find the other solutions. Wolfram alpha also does that. It looks like if one uses the quadratic formula on this part here, the r squared minus 2r plus 5 part, one gets 1 plus or minus 2i. So if we solve this, we get that r is 2 and also 1 plus or minus 2i. So what's our general solution? Well, from r equals 2, a real part, we have our ordinary e to the rx, e to the 2x, times an arbitrary constant c1, and then plus a linear combination of the two solutions from this complex conjugate pair, c2 e to the 1x sine 2x, plus c3 e to the 1x cosine 2x. And to be clear, I've color-coded where those pieces come from. So we have our general solution, 3 linearly independent solutions for a third-order differential equation. And finally, complex roots can themselves have multiplicity greater than 1. Let's take a look at this. The auxiliary polynomial here is this, a fourth-order polynomial, great fun. If one graphs this, you can see it has no real solutions. It never intersects the x-axis, but it factors like this. R squared minus 2r plus 2 all squared is 0. So if you look at the complex roots here, you might think, okay, it just has those 2 roots. But no, each of these has multiplicity 2 because it's squared. Let's go back to the slide and illustrate what we mean. So if one factors that, one ends up with this, said Wolfram alpha, and as one can verify by foiling this out. And this part here, if we solve for r there, we get that r is negative 2 plus or minus the radical of negative 2 squared minus 4, 1, 2 all over 2a, which is that square root of negative 4 is 2i. So we have 1 plus or minus I. So r is 1 plus or minus I, but with multiplicity 2 due to that. And in fact, if one fully factors this, it would factor as r minus 1 plus I all squared times r minus 1 minus I all squared is 0. So that's one root of multiplicity 2, and this is the other root also of multiplicity 2. Okay, now, r is 1 plus or minus I with multiplicity 2. What are the 4 solutions? Well, if you guess that it's the ordinary complex solution and then we stick x's in front, just as we did before for repeated roots, you are completely correct. So y is c1 e to the x sine x plus c2 e to the x cosine x plus c3 x e to the x sine x plus c4 x e to the x cosine x. All of the coefficients here are 1 because it's 1 plus or minus 1 times I. And that is our 4 linearly independent solutions to this 4th order differential equation. Those x's we stuck in front are because it has multiplicity 2. All right, so by combining all of these, we can find a general solution to literally any homogeneous linear differential equation with constant coefficients. In the next section, we'll learn how to do it for non-homogeneous differential equations, which will be combining our YH plus a YP. Remember, this is actually just YH because it's the solution to the homogeneous differential equation. So we'll learn how to get a particular solution, and then we'll be able to mash them together and solve non-homogeneous linear differential equations. I'll metaphorically see you next time for that. Have a great one.